Is conscious vision rich or limited? Intuitively, we may think that we see everything that is in front of our eyes. There have been some striking findings, however, that seem to challenge this view. You probably all know about that gorilla that you don't see, or other demonstrations of inattentional blindness. When you focus your attention on something, everything outside the focus of your attention seems to escape you. Something similar is observed in change blindness. In the images shown here, there are constant changes occurring, but they are surprisingly hard to notice, even though they are as large as doors, windows, or entire buildings disappearing. Observations like that make you doubt what you see, even in a simple scene like this. So, what do you see here? The simple answer, of course, is that you see a circular array of 8 objects. You can easily identify each of these objects, and you will have the strong impression that you take them in more or less all at once. But what when I take the array away and ask you again? In this case, you have to resort to your memory of the array, and you might notice that while you try to answer and sum up some items, that memory is quickly escaping you. You will find that naming all the objects in such a free report is virtually impossible. To alleviate the interference between memory and report, your capacity to take in and hold objects is often gauged using a change detection paradigm, which is displayed here. First, a memory array is presented, followed by some interval that may range from a few hundred milliseconds to a few seconds. Then, the test array is presented together with a cue pointing at one of the objects. Your task is then to say whether that object had changed or not, which happens in 50% of cases. Now in this case, it had changed. It went from a motorcycle to a frog, a pretty noticeable change in itself. Even so, if you let people perform such a task, it is found that they are very bad at detecting these changes, just like in the traditional change blindness experiments using natural scenes. Percentage correct is usually about 60% or so, while chance performance is 50%. You can convert this percentage correct using a formula designed by Cowan. The resulting number, K, equals the number of items that people apparently have taken in and remembered. And the 60 or so percent correct then converts into a capacity of 2 objects. Now once again, this confirms the idea that even though you may think that you see the 8 objects all at once, in fact you take in just a few at each moment in time, 2 objects in this case. Which these 2 objects are depends critically on where your attention is focused at the moment the array disappears. Because when you cue the item that might change in advance, so before disappearance of the memory array, percentage correct obviously soars to almost 100%, showing that the change in itself is not difficult to detect. The experiment seems to confirm that indeed conscious perception is rather poor and limited to what you happen to attend to. And that is indeed the way these experiments are interpreted by many authors. Influential scientists and theorists about conscious vision take these change blindness experiments as directly showing that although you may think that you see all the 8 objects in an array like this, in fact, you see only a few of them at each moment in time. They argue that you suffer from an illusion of richness, a bit like the illusion you have when you observe the light of a refrigerator. It seems always on because when you look at it, it is on. But in reality, it is only on when you look, and off otherwise. Same with conscious vision, they argue. You think you see everything, but that is only because when you look, meaning when you attend, whatever you like to consciously perceive is available to you. But is the richness of your perception really an illusion? You can do the change detection experiment that I just described slightly differently. Instead of presenting the cue together with the test array, you can also present the cue just before the test array, so at the end of the interval. In that case, the memory array has long disappeared as well, and if indeed you would only have a limited representation of the memory array items, your ability to detect the change would have to be just as bad. But that is not what is found. On the contrary, percentage correct is generally much higher in this case, and when converted into Cohen's K capacity, you end up with people apparently being able to take in as much as 5 or 6 items instead of just 2. This would then argue for something completely different. Your representation of the memory array does not seem poor at all, but instead fairly rich, holding as much as 6 of the 8 objects. So the story clearly is more complicated. Instead of the change blindness experiment simply showing that your conscious representation of an array of 8 objects is rather poor and limited to about 2 of those items, it seems that you also hold a much richer representation, consisting of the majority of the memory array items. Let's have a closer look at how these results can be explained and where these two representations may sit in our heads. When the memory array is presented to you, visual cortex will of course rapidly build a representation of the 8 objects in the scene. Some of these objects may be more salient than others, and they will draw your attention. Or you may choose to direct your attention at will at some part of the array. Either way, your focus of attention will highlight those objects. This will enable you to gain access to them, maybe report them, or to cognitively manipulate them otherwise. In the end, you may store them into working memory, which is of course closely linked to attention. Then, when the memory array disappears, the visual representation will shut off as well and will slowly decay as a cortical afterimage of what was presented. Now, the working memory representation of the few objects that you attended will remain present, however. Then the test array is presented. This will evoke a new representation in visual cortex that overrides whatever is left of the previous memory array representation. The cue, pointing at one of the objects in the array, enables you to focus your attention to the corresponding object representation in visual cortex and compare it to the representation you have of the object at that location in the previous memory array that you are still holding in working memory. And on the basis of that, you are easily able to detect that in this case there was a change. If, however, you happen to have attended at another location of the memory array, say some items on the left, you will have some other locations and objects being held in working memory. As a result, the comparison now fails, and you are at chance knowing whether there was a change or not. This explains the poor performance in the change detection task and shows you how the capacity you find when queuing subjects after presentation of the test array will give you the number of items that people can store in their working memory. And as said, this number is fairly low. Now, can we explain with the same account the high capacity you find when the cue is presented during the interval, even long after the memory array has disappeared? Let's go back to this view where a subject is waiting for the memory array to be presented. When the memory array arrives, again, a visual representation is formed. And again, attention will be drawn by some of the objects, but which those are is irrelevant for now. Then the memory array disappears. and the visual representation will decay and fade away, but this may take quite a while. Because when a cue is presented during this decay, subjects can apparently shift their attention to the decaying visual representation and store that particular item in working memory. And then, when the test array arrives, this will override the decaying memory array representation, and a new visual representation is built, now of the test array. But the item at the cued location can then again be easily compared to what was in working memory, and the change is easily detected. Can this then explain the high capacities that are found when the cue is given during the interval, even when presented long after the memory array has disappeared? Note that in order for this to work, the decaying visual representation of the memory array should indeed represent many or even all of the items. Because when the cue arrives, subjects do of course not know which item will be cued. So they have to be able to store the motorcycle when the cue is pointing here, or the pear when the cue is pointing here, or the flashlight when the cue happens to point here. That implies that after the memory array has disappeared, indeed, a full and rich representation of many or all of the objects has to be present for attention to select from, so that any of these items can be stored in working memory when cued. By the way, also note that such cueing has been shown to work up to 5 seconds after disappearance of the memory array, indicating that the visual representation that is selected from indeed decays fairly slowly. So that fully accounts for the high capacity representation that is found for trials when the cue is given during the interval. And it shows you how the capacity obtained using this paradigm gives you the capacity of the pre-attentive visual representation of the memory array, which seems to be fairly high. So, in sum, we indeed have two different representations in our minds when we look at an array of 8 objects as shown here. We have a visual representation, which has large capacity, yet which is also easily overwritten when a new scene arrives. And we have a representation of what is in the focus of our attention. This one has a smaller capacity, yet is stable and resistant to interference. When the stimulus is then taken away, the two representations, by definition, become memory representations. The attended items end up in working memory, and the non-attended items end up in a fragile form of visual memory, a sort of cortical afterimage of the image that was presented, decaying in a second or 5, and overwritten whenever a new scene is shown. Now note that although in the end, of course, in the change detection task, these memories are tested, yet these memories are a direct window on what was represented at the moment the stimulus was still there, and thus have a bearing on what we actually see in these scenes. Now, the first question you may ask is whether it is indeed the case that the one representation is depending on attention, while the other is not. Could it not be the case that subjects use different forms of attention for the two types of trials or for the two types of memories? And also, is it really the case that the fragile visual memory representation is a purely visual cortical afterimage? To test the role of attention in the two tasks, we performed an experiment where subjects were combining change detection with another task that also demanded attention. Subjects were shown foveally presented letters, 300 milliseconds each. Their primary task was to detect repetitions of these letters, a so-called ANBEC task. This task is known to demand a high level of attention to the letter stream to perform it correctly. Now, every now and then, an array of rectangles was presented surrounding the letters. On some trials, this array was meaningless, but on other, critical trials, this array was followed either by a queue and a test array, or a test array and a queue. And subjects had then to detect a potential change to one of the 8 objects in the array, very much like the experiments I already discussed. On those critical trials, the first array therefore was a memory array. Now, subjects did not know in advance whether an array would become a memory array or not, because in many trials the array was not followed by queues or test arrays. So the idea is that attention is taken away from the memory array in this way, also because subjects are urged that performance on detecting the letter repetitions is their primary task. In a separate block, we presented the same stimuli, but subjects were now instructed to ignore the letters and just focus on the memory array task, so that attention was focused on these memory arrays. Again, we calculated capacities for fragile and working memory as previously, and looked at the effect of attending to the primary task or not on these capacities. And as before, we found a much higher capacity for fragile memory than for working memory. Now, importantly, the working memory capacity was strongly affected by the attentionally demanding and-back task. The fragile visual memory capacity, however, was not. So, the experiment clearly shows the relation between attention and working memory and the independence of attention and fragile visual memory. In another experiment, we studied the neural basis of the 2 forms of memory by interfering with activity in dorsolateral prefrontal cortex using TMS. This part of the brain is known to play an important role in attention and working memory, and if indeed fragile memory is independent of attention while working memory is not, the 2 capacities should be differently affected by the TMS. We had subjects perform the change detection tasks with either post or retro cues, while TMS pulses were given during the interval between memory and test arrays. We found that working memory capacity, shown in red, suffered from the single TMS pulses on the dorsolateral prefrontal cortex, while fragile visual memory, shown in blue, did not. Also, repetitive TMS pulses, here 5 pulses at a frequency of 10 Hz, given during the interval, had a similar effect. This effect, by the way, was also specific for pulses given to the right dorsolateral prefrontal cortex, as identical pulses given to the left side of the brain had no effect on either working memory or fragile visual memory. To study the neural basis of fragile memory, we also recorded functional MRI activity in subjects performing the change detection tasks. We specifically looked at activity recorded during the encoding of the memory array, so preceding any queue or test array. And using retinotopic localization, we could isolate activity related to each item individually. We then sorted trials according to whether we could assume an item to have been present in fragile memory or working memory only. And we found that activity in visual area 4 in particular had a strong relation to change detection performance and more strongly correlated to an item being stored in fragile visual memory or not. Now, these findings hence strengthen the idea that indeed the fragile memory store is a remnant of visual activity. The relation between fragile visual memory and visual cortex was further confirmed in various other experiments. Here we applied transcranial direct current stimulation to the visual cortex, either by putting the anodal or cathodal electrode on the occipital pole. It is known that the 2 configurations respectively increase or decrease activity in the underlying cortex. And in accordance, we found an increase or decrease of fragile memory capacity during TDCS, depending on anodal or cathodal stimulation. Working memory capacity did not depend on TDCS stimulation. Again, the findings show a clear dissociation between the 2 forms of memory, fragile memory depending on visual cortex, working memory not. Finally, we looked at individual differences in fragile and working memory capacities, as these may differ between individuals in a reliable and reproducible way. We found that individuals with higher fragile memory capacities, here termed iconic memory, had higher gray matter densities in several parts of the visual cortex, as measured with voxel-based morphometry. These subjects also had higher concentrations of glutamate in visual cortex, as measured using spectroscopic MRI. Again, this did not correlate with working memory capacity. In sum, these findings strongly support the dichotomy of visual representations proposed earlier. There is a visual representation, depending on visual cortex, independent of attention, that holds many, if not all, of the objects of the array, yet which is fragile, in the sense that it is overwritten as soon as a new visual stimulus is presented. And there is a working memory representation, depending on dorsolateral prefrontal cortex, depending on attention, that has limited capacity, yet is stable to interference from new information. The main question we are addressing here is about perception. Let's not forget that. Now, can we argue on the basis of the findings so far that we see all the 8 objects, or at least 5 or 6 of them? Or should we stay with the notion that our seeing is limited, and that despite the rich visual representation, we only really see 2 objects? The fact that we have evidence for 2 representations, a rich one and a poor one, in itself does not pose evidence for either of the 2 views. And in fact, this is exactly how it is viewed by the limited perception proponents when confronted with this evidence. They have argued that fragile memory may indeed exist and may also hold many items. Yet, they argue, the items in fragile memory do not have the same quality as those in working memory and attention. It has been proposed that items in fragile memory are nothing more than a vague notion of blobs or shapes, a gist of the idea of 8 objects, without subjects really knowing what is out there. Now, this can be tested directly, and so we did. We used a change detection task as shown before. But after having responded to whether there was a change or not, we posed a second question to the subjects. On every trial where a change had been present, we also asked subjects whether they could identify the object that was present before the change. They had to select from 4 alternatives that looked more or less similar, for example, because they had the same general shape or color. Now, if indeed the items in fragile memory are just vague blobs, on the basis of which a change can be detected even without really knowing what object was there, this second task should pose serious difficulties. Now, for both the fragile and working memory trials, we calculated capacities, as we did before. But these were now split up in either high-quality objects, which were based on trials where subjects not only detected the change, but also correctly identified the pre-change object, and low-quality objects, where subjects only correctly detected the change, but were at fault identifying the pre-change object. Surprisingly, we found that the working memory capacity, again totaling to about 2 items, was made up of 1 low and 1 high quality object. The fragile memory capacities, on the other hand, were largely made up of high quality objects, with only 1 low quality and 4 to 6 high quality objects. In conclusion, fragile memory does not consist of vague blob-like representations of objects, but instead holds sufficient detail to really know what object was there. We further quantified the precision of the fragile memory representations in experiments where subjects had to indicate the exact orientation of objects they had seen. The memory arrays in this case consisted of arrows of varying orientations. After an interval, one of the arrows was presented again, and its location was either cued during the interval or not. This arrow then had to be rotated back to its original orientation by the subjects. Two things may happen. Either the subject has no clue as to what the orientation of the arrow at that location was, and then he will probably rotate the arrow back to some random orientation. That is what you see in this part of the distribution. Or the subject does know what the original orientation was and will rotate it back to that orientation, in this case 40 degrees away. Of course, there will be some margin of error here, which is the width of the Gaussian of this part of the distribution. From the height of the distribution at minus 40 degrees compared to the rest of the distribution, we can then gauge the percentage correct, and hence the capacity of each representation. And from the width of the distribution at minus 40 degrees, we can gauge the precision of the representation. And we once more replicated the finding that fragile memory has higher capacity than working memory capacity also in this task. But both fragile and working memory had equal precision. So the idea that only attended representations are precise, detailed, and hence fully perceptual, while fragile and unattended representations are vague and merely gists of objects, is incorrect. High-capacity representations do in fact not differ at all in these respects from low-capacity representations, or may even outperform them. This obviously strongly counters any arguments to disregard high-capacity, unattended visual representations as non-perceptual. Another argument that has been made is that high-capacity fragile representations may be precise and detailed, yet that this only happens at the moment that attention is transferring the item from fragile to working memory. The argument states that before attention, items in fragile memory consist of unbound features, freely floating in perceptual space, without being integrated into a coherent object representation, and that only attended objects are fully integrated. Now, does this make any sense? Already in our very first change blindness experiments, we observed that the higher fragile memory capacity is found just as well for objects that are defined by the integration of features. Here you see an array of 8 rectangles that are solely visible, however, because your visual system groups all the line segments that have the same orientation into rectangles and segregates those rectangles from the background where the line segments have another orientation. Seeing these objects thus crucially depends on the integration of features into coherent objects, segregating from each other and from the background. You cannot know the orientation of the 8 rectangles if the line segments that make up these rectangles are not integrated and just stay freely floating and unbound. Yet the higher capacity for the fragile memory representation compared to the working memory representation is found just as well using these stimuli as for objects that are defined by luminance or color contrast. It is about 6 to 7 objects compared to 4 for the working memory, very much like in the other experiments. A similar experiment is this one. Here we presented arrays of Pac-Man. These Pac-Man were organized such that in some configurations they formed conical triangles, while in other configurations they did not. Obviously, perceiving the Pac-Man as conical triangles will enormously facilitate the detection of a change in the array of Pac-Man, as is illustrated here. In the conical condition, one can simply detect a change in the orientation of the triangles, while in the control condition one would have to scrutinize the orientation of each Pac-Man individually. If fragile or working memory representations holds items in a form following a modal completion of the Pac-Man and inference towards the conical triangles, we expect a huge increase in performance for the conical versus the control condition. If items are stored as loose and unbound features, however, devoid of any amodal completion or perceptual inference, such a benefit should be absent. What we find is the former. Both for the working and fragile memory conditions, there is a large benefit for the conical compared to the control condition. The benefit is even larger for the fragile memory condition than for working memory. So this unequivocally shows that items in fragile memory are represented in a stage where grouping, amodal completion, and perceptual inference have taken place. So also the idea that items in fragile memory are stored as loose and unbound features is clearly incorrect. Instead, items in the fragile high-capacity representation are fully integrated and have perceptual qualities like amodal completion and perceptual inference. So, in sum, we have shown the following. When you look at a scene like this, consisting of an array of 8 objects, you form 2 distinct representations of it. The one is a visual representation, which has a high capacity, which is independent of attention, depends on visual cortex, and therefore is easily overwritten when new visual information comes in. The other is a representation depending on attention and dorsolateral prefrontal cortex, which therefore has limited capacity, yet is stable against interference from new information. Importantly, the visual representation is not only rich in that it has high capacity, but it moreover holds items in great detail and precision, like that, or even better than the items to which you attend. The items are represented here as integrated features and show full perceptual qualities such as amodal completion and perceptual inference. So what does this say about conscious vision? One could still argue, of course, that such a rich, detailed, and perceptual representation of many objects is nice, but given that you cannot attend to all this richness, it is therefore not conscious. In my view, that ends all scientific discussion and argumentation, because you then simply equate consciousness to attention. You equate consciousness to the ability to report about conscious experience. You equate conscious experience to access and storage of that experience, and you do so by a priori definition. I have a simple question for you if you want to do that. And that question is, why? Why is conscious experience the same as reporting about it? Why is consciousness attention? What exactly does the attention, the cognitive access, or the reportability explain about conscious experience? How does it explain the qualitative aspects of seeing? Because what more is necessary to explain conscious visual experience, to explain visual qualia, if you like, than perceptual properties of visual representations? If these don't explain visual experience, then why does adding attention or report suddenly does? Answer these questions for me, please. Answer them before you start robbing people from the idea that they see all the 8 objects in a scene as shown here. Answer these questions before you start robbing people of the idea that their perception is rich and detailed, as it introspectively seems. Because that is what the conclusion should be. Your intuition was right in the first place. You do see all of these objects at once and in detail. Don't ever let any gorilla or psychologist with funny experiments convince you otherwise. I would like to thank these people for performing many of the experiments that I have shown here. I am supported by the Amsterdam Brain and Cognition Center, and much of the work shown here was funded by an advanced investigator grant from the European Research Council. Many thanks for watching, whether you attended or not.